if you ever seen like a stack of plates, that's the way that we can think of a stack. So this is normally how a stack looks like. Is let me draw it a little bit. Sketch. So usually a stack looks like this. A stack is a data structure. As I said before, this is linear, i.e., this is a nonlinear data structure. A tree is a nonlinear data structure. A stack is a linear data structure because elements can be seen one followed by the others, and there is no hierarchy between the elements. And the stack have only one single point of entry, which is this one. And you can't take or add elements in here, and you can't random access elements. So arrays, for example, when you have an array that has elements, we say that arrays are random access data structures, because I can say at any point, give me array of 0, give me array of 2, give me an array of I. And basically, this will be the array will provide you with the element in that array. One moment. I'll mute. Okay. And the array data structure is a linear data structure, but it supports a random access. Stack does not support random access. So you can only add elements in one location, or you can remove elements from one certain location. So adding elements, so if we have a stack like this, and we have a stack can be of some elements, through the whole presentation, I'm gonna design and code and talk about stacks of integers, but basically the basic concept like stays the same for stacks of any kind of type. So if we want to add number 1 to the stack, it's usually we can imagine that there is nothing in the stack, and then we put it in here, so it pops up in the bottom. And we add 2 in the stack, it just throwing something into a vacuum, and then it falls into the next available slot. And 3 is kind of the same. We're gonna add 3 and then add 10, and it's all the same. So we only can add from one certain location. And removal can only be done from one certain location, which is the top of the stack. So if we have a stack like this, and we have some elements in it, as I did before, I can only remove the top element. So in this example, if I say like remove from the element, I can only take 10. I can't access 3 before removing 10. And I can't access 2 before removing everything on top. So I can access them in this order. So I can only take 3, take 3, take 2, and then take 1. Is this part clear?
Yes.
Okay. So I was saying, yeah, you will hear, when you hear stacks, you will hear about something, an acronym that calls LIFO, which means last in, first out. And this is just a mnemonic to understand and to memorize the order in which the elements are added and removed from the stack. So we all if we add elements, like if I add 1, 2 like this, when I want to remove, I will remove the last element that has been added, which is 2. So I will remove 2, then 1. So always the last element added will be removed, and then the next one, and then the next. So this is what LIFO will refer to. And there are mainly 2 or 3 operations, and you will find like a stack will support, in most programming languages, 2 operations. So this is the stack. It will support adding an element to the stack, which is like push element, or it will support pop element. And pop should give me the first element. There are like some variants, like you can do peek on a stack, which means give me a reference to the first element, but don't remove it. An example of this, imagine having a stack that is empty. If we call push 1, we will add, and we call push 2, we'll add 2 to the stack. If we call peek, we will return 2. If we call pop, we will return 2 again, but this time 2 is going to get removed from the stack. And the next time we are going to call peek, or we are going to get 1. Is this part clear?
No, could you repeat that?
Okay. Yeah, which part is it's not clear? Is it the peek, the push, or the pop?
Peek.
The peek. Okay. Okay. So peek is as the name kind of inscribed. So we have 1. We have some elements in the stack, and when calling peek is just pop, but it doesn't remove the actual element. So when I call pop, I actually remove the element. When I call peek, I get the top element, but I don't remove it. So calling pop will give me 2 and 1, and the stack will be empty. But if I call peek, the first time I will get 2, peek. The second time I will get 2, peek. The third time I'll get 2. So the top element never changes because I'm only interested to see what's on the top of the stack. Eddie, is peek clear now?
Yes.
Okay.
Thank you.
Okay, cool. All right, and stacks can be bounded. They are bounded data structures in a way that so imagine having a stack. So as I said before, I can always push elements to it. And bounded stacks are stacks that have a certain capacity. So let's say I create a bounded stack that has a capacity of 3. So when I call push the first time with 1, I can add the first element. Push 2 will add the second element. Push, let's say 13, I will add the third element. But when I call push with some kind of value, nothing will happen because the stack is full. Okay? So the stack never grows and be like and be bigger actually than the capacity. We can never have the size of the stack bigger than the actual capacity of the stack. So that's why we call it a bounded stack, because it doesn't grow indefinitely. Because in the abstract definition of a stack, the size is never mentioned. So you can theoretically keep calling push until you ran out of memory. But if you want it to be bounded, and sometimes you do, the stack can be bounded, and operations that go beyond the capacity of the stack are ignored by the implementation or generate some kind of exception, no matter what the exception is. Is this part clear about bounded stacks? Because it's the same thing for bounded queues.
A question. That means that before I have to initialize the stack, right?
What do you mean initialize?
Just put the size of this stack, for example, 3.
Yeah, exactly. And a bounded stack, you should know the size beforehand. If we say bounded, you already have an idea about what's the maximum size the stack can get.
Okay.
We'll see an implementation of this, and if it's still not clear by then, I'm happy to kind of repeat that. All right. So in a stack complexity analysis, as we saw earlier, there are 3 main operations. So let me do something here real quick. So peek and pop are basically similar because we're only going to get a reference to the first element. And push should be done in constant time. Pop and peek should be done in constant time, and size should be figured out also in constant time. Can anybody see why do we have why everything can be done in constant time?
Because just have an instruction.
Because what?
Have just an instruction. Every of that command, push, pop, pick, size, have just instruction.
Yeah, but it depends. It can be like we can implement push and pop and peek, and we can implement them in something that is bigger than O of one, depending on the backend data structure. If you choose the backend data structure poorly, you can end up with something that is bigger than O of one. But in the standard implementation, and what you should expect from a stack or a queue is that to have the push and all the basic operations be done in constant time. So, all right. So implementation-wise, most programming languages have damn autocomplete. Have some kind of implementation in the standard library. So if you do C++, you do Java, if you do, I don't know, Python, any other language, you will have some kind of stack implementation. This is not available, I guess, for C. I don't think C has it in the standard implementation. But for other languages, it's pretty common to have stack and queue implemented in the standard library. And the implementation itself can be based off of two things. It can be like a linked list based implementation, or it can be a resizable array or a vector, so to say. In today's like presentation, we are going to do like a stack based off a linked list implementation and a queue based off a linked list implementation, just so you can get an idea of how this might look like. So who doesn't know what's a linked list?
I know a little bit, but I would like to do more deeper in linked list. I just know the basic, yes.
Yeah, so only what you need is you only need the basics, because you only need to support one kind of operation, and I'll kind of explain on it a little bit. So let me sketch it out. So basically, how we implement a stack using a linked list is having so what's a linked list? A linked list is like can be seen like this.
Yes.
Where each element kind of points out to the next element in it. And every element has some kind of data and has a pointer to the next element in it. Right? And then we can identify this data structure by having some kind of pointer to the head element. And we can like reach every element from it. The stack can be seen as from here is, okay, so we can add elements in here. And then we should be able to remove elements also from here. And if we can do that, this is a correct implementation of a stack. So if I have a linked list and I only add elements in here and I only remove elements from here, it's safe to say that this can be done in O of one, because adding elements in a link, removing elements and adding elements in a linked list is constant time, because it's only pointer arithmetics. So you're only doing like pointer assignments, and you're not actually and this is constant time. It can be done in constant time, and you're not actually doing any traversal. So in a way, you can do like you can implement a simple stack by having one single linked list that supports two operations, which is add first and remove first. is this like clear why this works and this works as a stack, and this works as all of one per operation?
Yes, that's clear.
Okay, so let's try. So let's try to do this. No, I don't want to leave this side. So let's write a linked list implementation that can support both operations. So let's have a list node. I will write a standard one. I'm afraid C++ already has, like, I guess, so already has a stack implementation, but we will try to write our own. So each list element should contain the data inside, and should contain a pointer to the list node, which is the next. Right? Okay, and this list node element should give us like some utility methods, like get value, get data, and should get us the ability to get next, so we can like know does it have a next element or not, and should also give us like set next ability. Okay, and now we should be able to write the linked list class. And a linked list is nothing more than a pointer to the head element. And it should support, we said that it should support, so I will create it from a constructor, and we want to keep track of the size. And we should be able to add elements, which is like push. Add first. And remove first. And peek first. And a stack will only delegate these operations to it. So a stack, in fact, is nothing but a linked list. So we can have like a linked list. And this is the stack, actually. So I should probably write some kind of this structure for this, but I'm not gonna bother, because this is like for this demonstration purposes. And a stack is basically a new linked list. And when we do like push some element, it's just add first element. Yeah. And when doing like int peek, it just stack that peek first. And when doing like int pop, I said pop, right? Return stack. And that's it. This is like a stack in all its glory. So going back here, this is like implementation related to the add first, but we'll try to do this. As you said that you wanted to know how to implement this. So adding a stack, an element at first is like just checking if the head. So either we don't have anything in the queue, and head will be just a new list node for the given value. Otherwise, we should add element to first, or we should create some kind of new node with the given value, and say that the new node that's set next is the head, and the head is equal to the new node. And at each time we add an element, we should increment the size. To say like, hey, we added a new element to the list. So this is basically equivalent to saying this. We have a data element. So we have this is like the current head. If you want to add, so this is the next part, and this is the data part. And at first, when pushing to the first element, this is null. We don't have a head anymore. We don't have a head yet. So at first, head is null. Head is pointing to actually nothing. So at first, when we add the first element, head will be equal to the new created element, which is some kind of data, or say 1, and nothing in here.
Next to the pointer, no? Next element. Pointer to the next.
No, the head is the first is gonna be pointing to the first element. So head and the first element are actually the same pointer. And the next element is actually null. And at the second time you are going to try to add it, you will have 1, and you should keep here null. But you should create a new element and add 2 in it, and make the next of this is the actual head. And then make head point here. And now this is head. So this is like add first. So if you remember, you want to add supporting adding here. So if you have 1, after adding 2, you should get something like this. Is it confusing?
A little bit, because the first pointer is first null, right? When the first element is created.
Yep.
Now the header, where is pointed the header? The header is pointed to the first element that was created. Then are you creating a new element here with 1, and the next is going to pointer to this element. So then this last element 2 is going to pointer to the same element 1 there. Why?
It should, because you want to keep. So to have a linked list, you should have something like this, right? If you create an element and don't make it point to something, then that even means there is nothing after it, right?
Right.
So in this case, we have something like this. So I guess you're confused in the second part, after adding 2.
Adding 2, yes.
Yeah, so we have head, right? And head is just a pointer that points to this. It has 1. Now we want to add 2, and 2 in fact is just like this, right? At first, when we create it, it doesn't have an X, it doesn't have a previous, no one's pointing in it. We just have it in some kind of temporary variable, which is this. No assignments have been made yet. So what we do first is make 2, make this one point to the head. So we make the successor of 2 is actually 1, right? And then for this one to be the first element, we make 1 head kind of point here. And then we get this nice sequence of head, 2, 1.
Right. Mm-hmm.
Is it clear?
Yes.
Okay. So this is what I did here. So I created this temporary list node, and I set next to head, and then head is now the new node. So I take the list node and I said its next value is the actual head, and the actual head now is the new node, which is what I did here. So head at first should point to the actual head. This is the new element. You should point to actual head, because pointing to this or this one, it's the same thing because both are head. And now head should be this element. And then we add in 3 now, let's say. So 3 should point to 2, and head should point to 3.
Mm-hmm.
And this was gonna happen like later on. Okay?
Sí.
Okay, so let's do remove. So how does remove work? So I want to remove from the first element. And actually, if we have an element that is like this, so if we actually have some kind of element that is doing like this, and we have head here, all we have to do is, okay, so I don't want to see this anymore. I want to like point directly here. And that's it. So remove first is actually pretty easy because we want to see what's head actually pointing on. So removing an element, we have a list like this. And then head is here. 1, 2, 3. We want to remove this element. All we have to do is like take this and make it point here and delete this one. Does it make sense?
Yes.
Okay. So to do this, so all we have to do is if size is equal to 0, don't do anything, right? Because size is equal to 0, there is nothing to do.
Yes. Yes.
Head should be null pointer. And otherwise, we should take the this is like the first element equal head. We should point to head and then say head is equal to head get next. Now we change head, but we need to keep a reference to this, to the first element, and remove it. And then delete the first element. And of course, I should get the actual value. The first element value is equals to first element. And we should return. Okay?
Okay.
Is it confusing? If it's confusing, just stop me.
No, it's okay.
All right. So peek first is not gonna be any different from remove first. So just copy it out and remove stuff that actually are destructive. So if size is equal to 0, we want to signal that there is nothing. -1 in this case is kind of a signal that, okay, there is no element. And now we want to, if peeking, we will only need a reference, the value in the first element. So all we have to do is just return the value of head. Because a peek is only like, tell me what's the value in here. This is peek, right?
Mm-hmm.
All right. And then we have remove. One thing we should note is after removing, we should decrement the size. Okay?
Okay.
The size should be decremented to accommodate for the lost element. And now the stack is now our stack is complete. So what we're going to do is write a little helper function to print out the list. So I'll write it here. Okay. For some reason I have. All right. So what I'm going to do is like I will try to write a function that's gonna print this nicely. So I'm gonna do a first equals false and equal true at least, and noise is gonna be something of this sort, and stack dot. So we have stack, right, which is the internal implementation. We'll have like a stack, a list node, a linked list. Just like list equals st.stack, and we should get the. I guess it's better if I do it this way. So I'll do this. So I want to do this. And I'll do the same. And I'll do the same thing for the list because it's more obvious for the list. This is the linked list. Oh, for some reason it's not working. I want to copy and it's not letting me. All right. And I'll override the same function here. And here, I want to print it nicely. So I want to get the head reference. I want to just point to the head without actually changing it. So while head is not null, or it's not null pointer, I want to just append. If it's a first element, I want to add in first is true, equals false at least. And we want to add the head get value and head get next. And then we want to add the closing and return OS. Right? So this is just like for pretty printing and nothing like more specific. Now we can create a stack for some value and do stack.push 10. Let's do 1 stack. Let's do this. For int I equals 1, I smaller than 5, equals I. We can do like s.push I, and we can print out the stack value. And if we run this, probably it will work. For some value, it does not work. Right. It's just printing out the address of stack. Okay, live.
That should be show the value, right? The value.
Yeah, that should actually like print my list in a nice fashion, but the way I defined it here. But for some reason, I'm not getting that. Oh, I guess I know why. One moment. Where is that? I guess it's for this, probably. That was my bad. So I added 1, right? And then I added 2, and then I added 3, and then I added 4, and then I added 5, right? Now let's try. Now let's try do the same thing, but now we are going to reverse, and then like that's pop this time. We're going to remove the element, and we're gonna print out remove element. Come on, what happened? What the hell is he doing? All right, for some reason. It blocked for some reason. And we're gonna do like removed value. And each time we're gonna remove some value, we are going to print it out. So this time we removed 5, and this is the stack, how it's look like. And we removed 4, and this is how it looks like. Remove 3, and this is how it looks like. Remove 2, and this is how it will look like. And after removing 1, the stack is empty. Okay?
Okay.
So does it make sense up until here?
What did you do was using stack into the linked list, right? To start to push and push new values and remove. Mhm.
So push is like add. I just said before, push is just add in first to the linked list, and peek is just remove. Pop is just removing the first element from the linked list. So if this is the linked list, removing the first element, we'll leave it like this. And this is pop. So imagine that the stack's boundary is here. So add elements from here and remove them from here. So every time I'll add, I'll be adding from this side. Every time I'll remove from this side, right?
Mm-hmm.
So in this time, we pushed 5 elements, and then when we removed them, you can see like the order in which they were removed. And now I'm gonna do, instead of doing pop, I'm gonna do peek. Can you tell me what's gonna happen?
It's not going to remove. It's not going to remove. Just keep the value there.
So what's the output that you expect?
The same. I think the first, for example, remove value 5 is just 1, 2, 3, 4, 5. Or
Exactly.
oh, okay.
So peek actually is not gonna remove the elements. It's just gonna keep giving you 5. And sometimes when you wanna know, like just to know the top. So if you wanna say it's okay, so if it's if the first element is 5, remove it. Otherwise, I don't want to remove it. So we want to say like, so if value is equal to 3, pop it out. Just break, right? Otherwise, pop it out. So in this time, we are going to say like, hey, I'm gonna remove 5, and then I'm gonna remove 4. But the moment I reach 3, I stop. If I didn't have like peek and I only had pop, this wouldn't happen because I will be shorter an element, right?
Right.
And then if I print my list here, I will find that I'm missing an element. I actually only have to 1. Because if I don't have that utility method that only gives me like the top of the stack. Well, I hope this was like clear now. We can move on to the queue part, and the queue part is not that hard. If you understand stack, most likely you'll understand queue. We'll only change the implementation.
Okay, let's continue.
So right, do you want to have? So I will try to. So let's start to add a little bit of documentation. So this is a list node to keep track of element node linked list elements, and we'll have a list of list node, a standard implementation of the a linked list with singly linked list. I'll just say linked list. Linked list. And to make it a little bit easier to visualize, I'm gonna say like data next, data 2 next, data 3 null, right? This is the implementation that we have, and we have had. And the last part, which is a stack will consider the first element as the boundary of the stack. And we only are going to remove from the first, remove the first element, or add to the head of to the start of the linked list, right? So I guess this makes sense. For this, add an element to the stack of 1, and show see the first element in the stack without removing it. In of1 also, and popping out is like removing the first element in the stack with removing it and returning it in of1. Now, hopefully this is clear now. I'll say, oh, come on. Please don't make me sign up. Copy. I guess this is shareable now. Okay. I'll add it into the resources section.
Thank you.
I don't know what's the resources section here. So there is resource Java, resource C. There is no resources for algorithms. Probably should have been a good one there, but well, I'll add it into the post, and you can guys like, and you can read it there. Hopefully, you can read it from the next course part. References for stack and queue lecture. So I put it in there, and yeah, you can like check it out. Now let's move on to queue. So a queue is also a linear data structure, and a queue, as the name refers, you can see it as a queue, like in the entrance of a shop. You will hear the acronym FIFO, which will mean like something that is like this. So a queue normally is like this, and this time, this is bad. So a queue is like this. But remember that it doesn't have this boundary, right? And here it doesn't have that boundary. So I can add from here, and then I can remove from. So the queue is like, you can add through here, and then you can remove from here. And the stack, we were only able to remove and add from the same point. But in a queue, you add from here, and then you remove from here, just like a normal queue. You have people coming in from one direction and going out from the other direction, right? So if this is a shop, then you have people coming in lining up like this. People come from here and they are served from here and like going away. So in our case, you will hear like the FIFO mnemonic, which is like first in, first out, which means basically that if we add like elements, like I said, from here we have add and remove. So if I add 1, and then I add 2, and then I add 3, and I remove them from here, so I will remove 1, I will remove 2, and I will remove 3. The first one that came in is the first one that got out. The second one that came in is the second one that got out. The third one that came in is the third one that came out, and etc. etc. Is this part clear? I get Q is more easier to understand, so to say. If it's not clear, I can repeat.
It's clear.
All right. Okay, so in theory, it supports the same kind of operations, and it can be bounded also. I didn't do a bounded implementation of a stack here. Do you want me to add the bounded operation support?
Yes.
All right. So let's go back to stack. Yeah, it would have been better like if you would have like made me remember that I forgot actually about a bounded stack. So let's do this. I will write a class. You can write a bounded stack however you feel like. I will write the simplest bounded stack that I can write. A bounded stack is just a stack. So you can do inheritance. You can do it however you feel like, but I will have a stack here. And this is the bound. This is the size. And then I will have a bounded stack and size. And this is like, and this should be like the bound. And now we can copy out all the implementations and say like, I have a stack that is equal to a new stack, just as we did before. But this time, we will have like 3 operations. And oh my. This is it. And this time we are going to do so push. We are going to this process is called delegating. If you're not familiar with the concept, so we are going to delegate to an existing implementation, such as we did with we did pop in here. But the cool thing to note is we need to do some bound checking. So if the stack size +1 is still smaller than the bound, so it's smaller than the bound, we can add this, right? I don't have a stack size method, which I should. What's the thing? It's the length, I guess. It's the size. Okay. It's the stack size. And then we'll have a method that's called element count. That will basically just return the size, right? No member in linked list. So this is a stack. Where did I add a method? Element count. Right? And now we have a size. And now we should know that if the stack that size, if the size is smaller than the bound, we can add it. But if the size already have reached the bound, we can't add new elements. We can't add new value. So bounded stack is simply a stack that a bounded stack simply a stack that has a fixed size and cannot grow bigger than that. So if we have like a stack already, and we know the size, we should always create a bounded stack with a bound. And as long as we are below the bound, we can add it in. Otherwise, we can't add it. But the other operation stays the same. So to illustrate this kind of, instead of creating a stack, I'll create a bounded stack. And to create a bounded stack, I should give it like some kind of bound. In my case, I will give it like I only want to add 4 elements, right? And I need an operation for the bounded stack, which I'll do the same. Well, I could have gotten one with inheritance, but I don't want to make my methods virtual. Bounded stack. And I should add it as a friend method. Mm-hmm. Now, if I run this, 4 is never removed. 5 is never added because the bound is 4. And once we have 4 elements, we can't add new elements to it. Can you see the difference between a bounded stack and a stack? Or is it obvious or not? So if I put the bound here as 3 and I run it, whenever I call add, 4 and 3 will be ignored. 4 and 5 will be ignored. So here I can never add. So I add 1, I add 2, I add 3. When I try to add 4, I can't because the stack is full. Okay?
Okay.
So this is like the difference between a bounded stack and a normal stack. I will share this also so I won't lose it. All right. All right. Now let's jump into a queue implementation. So a queue can be implemented with a stack, with a list also, with a linked list. But in our case, we want to implement it with an array, just for the sake of the experiment. So do you know what's a vector or a resizable array?
No.
Really? So a resizable array is just an array that you can that doesn't have a fixed size. So you can add to the front as you can add you can remove from it, and you can add append element to it. That's just so you have an array that kind of grows as you need it to. So this is dynamic array. So if you have an array like this, so you start off with an array that has 0 elements, and you can add 1 to it, and you can add 2, and you can add like, and you can remove like 3 from it, and it will be like 1, 2, 4, and you can remove like 1 from it, and it will be 2, 4. So it grows and shrinks however you like. And I'm not gonna bother writing one. It's a little bit toily to write a dynamic implementation of this, and the complexity analysis for this, we want this to be like very fast. So I will need to explain the why do we shrink or why do we grow in a certain manner. So to not do this, I will use something from the standard library, which is a vector, and a vector is simply a dynamic array. Yeah. And I will use it to implement the queue. And a queue is nothing less more than a vector. So our queue can expose like as the other one can expose like methods such as push, pop, and pull. Actually, pull and peek. So pull will remove the element, but peek won't, and push will add elements to the queue. So the array like this will act as the queue. And this is the queue, and when we add elements, we will add them to the back, right? And if we remove elements, we will remove them from the front. So when I call remove now, it will be like this, right? Or do you want to do it the other way around? You want it just to add to the front and remove from the back? What do you want?
Just remove the front.
Okay. So let's do this. So push now is easy. I'll just go queue that pushback value, right? Because we're only pushing to the end of the array, and this will grow as needed. Now peek will just we'll just see if queue that size is equal to 0. So if it's empty, we should just return -1. There's nothing to peek. Otherwise, we can return the first element in the queue, because we add from the back and then we pull from the front, right? And the same check should be done here. If the queue is empty, there is nothing to pull. Otherwise, oh yeah. So I can get the front allocator. Okay, so I'll just like erase queue dot begin queue dot begin +1, I guess. So what I did here is like I removed the first element, and then I added a and then I returned the first value that was there. And then I can even go and just call peek. And then remove the first element. Is this clear or it's tricky?
It's good. It's okay.
Okay, so you understand this. So let's try to write code for this. So queue is, we can like do the same thing. Do queue dot push I, and then and probably should write a friend function here too. Friend stream. And queue. And then I can do like os dot and for int I equals 0, I smaller than q dot size versus I. If I is bigger than 0, in this case, os dot and this. So we have q dot q, I guess. Yeah. Q dot q of I. And if I run this now, we can see that we added 1, we added 2, we added 3, we added 4, and then we added 5, right? So let's try like doing the same thing, but now removing it. queue.poll elements removed elements. And if you run this, so we removed 1, and then we removed 2, and then we removed 3, and then we removed 4, and then 5, right? So 1 is added first, so 1 was removed first. 2 was added second, and 2 was removed second, and etc. until 5. And if we called big, again, nothing should change. We should only keep saying 1. Right?
Right.
Okay. So now let's add the last part of the code, which is like implementing a bounded version of this. And what I'll do this time is instead of having another class, I will do the bound as part of it. So I'll do like int bound in here, and they'll have 2 constructors. So the queue should have, you can create a bounded queue by having a bound. And if you have the bound as part of the constructor, you can initialize the bound. And if you don't have the bound, we'll say that an unbounded queue is something that is so big that it reaches int max, or just very big value. Simulate unbounded. And I'll create this constant here, just for reference. Let's say it's 1 to the 30. And say that this is the bound. Because we know that we are never gonna reach this value because it's so big, it will feel like that the queue is not bounded. And if we give it a bound, we will initialize it with a bound. And here, whenever we try to push, we need to make sure that the bound queue.size is smaller than bound. Now add this. And this is all the changes that we are going to need. Right? And yeah, now we have an unbounded queue, and it should work as expected. And I do poll here. It should work as expected. And when creating a queue, if I say like as before, that has only 3 elements, it will only work for the first 3 elements. So I can only add the first 3 elements, and it won't grow after that. Is this clear?
Yes.
Okay, are you sure?
Not exactly.
So what's confusing?
Because I see here in this example, you are putting 3 things in one example. So I am just in this output, I am just confusing what is from the linked list, what is for quiff, and what is for stack. So
yeah, so this is so this is only queue stuff. There is no stack here.
Oh, okay.
So this is only the queue stuff. So we don't have stacks here. Only have a queue which has a bounded, that is bounded by 3, and then I add stuff in here. I left the code here just for reference for you, so you can like look at it later. But I'm only using like the bottom part, which is like the bounded queue. And I try to implement stuff differently each time, so I can tell you like, hey, you can find then a stack that is bound on a linked list, and it can be bounded and it can be unbounded. And to implement bounded, there is like 2 or 3 or 10 different ways to do it. And this is some kind of the ways that you can do it, right? And in this case, a bounded queue, like here I created another type that is called the bounded stack. In here, I didn't have to. I just added the bound as part of the creation construction and simulated a very big value with a very big value. And that I know that I will never be able to store it in memory, let's say.
Okay.
And here, if it's the queue is bounded, it will stop at 3 because I created 3. If I say 1, it will only be able to store 1 element. each time. And if I say it's 10, which is like bigger than the actual elements that we are trying to go to say, it's not, there is no there. So there is no actual difference between them. I can like, now I will add all the 5 elements and it won't change anything. But if I reach, let's say 15 in here, it will only store 10 and it won't go beyond that. Okay?
Okay.
Any questions?
Yes. So doing some more general questions. This is stack, no, Quiff, in which scenarios we can use just with linked list, we can use with other things.
It depends. This is like pretty language specific. So usually you won't have to write these yourself. These are pretty standard, as I said, data structures. They are implemented in every language. As I said before, like if you're using C++, you'll find like include queue and you'll include stack, and you will be able to write like this is a queue of ends and or this is a stack of end, right? And you won't have to write it yourself. And even a linked list, I guess, if you do include list, you'll have a linked list implementation if you want to. And this is like similar for pretty much every single language. They come with this baked in. Now, when to use linked list or when to use an array, that's actually a matter of preference and a matter of performance. So I don't know if I should explain this, but like, let's say a linked list would be good for to be like more memory efficient, and you will get more guarantees push and pop operations in terms of performance, because you won't have to resize at some point. So you will have like more consistent results if you benchmark this. But if you see like you're iterating and you're kind of navigating through the whole queue or stack thing, each time you don't have a good data locality, if you're familiar with the concept, because you have pointers all over the place. And well, if you have an array based, you'll have elements that are sitting next to each other. And for CPUs, this is like easily predictable. But this is like you shouldn't like interest yourself with this. This is not something that you should care about at this level. And all you need to think about that there are mainly two ways to implement a stack in a queue. A queue, it can be a linked list or it can be an array. With an array, this is how you can implement it. And with a queue, with a linked list, this is how you can implement it. What I encourage you to do is like, I implemented a stack using a linked list. Try to implement the stack using an array, and try to do the same for the queue. Try to implement the queue using a linked list and see if you can get it to work for both of them. I left you the code as a reference, so you can use the linked list class. And if you think that you couldn't make it, you can always like ask me around and see if I can like if I can help you in any way. Okay?
Okay.
All right.
Okay.
So any questions? And once you feel like you're comfortable using stacks and queues,
No.
and you feel like you can write your own, I can give you like some exercises that you can do.
Oh, yes, I will appreciate that.
Yeah, and I'll give you like some couple of exercises that you can use stacks and queues to kind of solve those problems. I will give you like a couple of easier problems that are pretty famous for using stacks or using queues, and you'll leverage the power of stacks and queues to implement them.